In this presentation, we will describe our approach for polynomial approximation with non-uniform segmentation for bivariate functions. This work has been done at INSA-REN and IETR laboratory. With the higher performances offered by modern computation platform, more complex applications can be implemented in embedded systems. Numerous applications in domains like signal and image processing, telecommunications, robotics use more and more complex mathematical processing to provide innovations. Especially, these mathematical processing integrate complex mathematical functions composed of several elementary functions. The challenge is to implement these mathematical functions with enough accuracy and without sacrificing the performances of the application. The memory footprint, the execution time and the energy consumption must be minimized. In the context of scientific computation, mathematical libraries, like lib-m, provide implementation of elementary functions with a high accuracy. The approximation error is low. This high accuracy is done at the expense of a high implementation cost and can be relaxed in the context of embedded systems. Moreover, the genericity provided by this kind of library is not interesting in the context of embedded applications. Indeed, we prefer to have an efficient implementation for a given mathematical expression. So, a dedicated approximation is more suitable. For univariate functions, various techniques have been proposed. You can use iterative methods as the shift and add BKM algorithm or the Cordic algorithm to approximate trigonometric, logarithmic, exponential or hyperbolic functions. These approaches require pre-computed tables. The accuracy will depend on the number of iterations. If low precision is tolerable, lookup table or multi-partite table methods can be used. These approaches require pre-computed tables and only addition operation which lead to efficient hardware implementation. Polynomial approximation is a good alternative for function evaluation, especially when several elementary functions are combined. A complex mathematical expression can be evaluated with a dedicated single approximation. Tools, like Solia, use Remma's algorithm to determine the optimal polynomial coefficients to approximate a function f, on an interval I, for a predefined polynomial order. The maximum error between the polynomial and the approximated function is minimized. To increase the accuracy, the initial interval can be split in smaller sub-intervals and a polynomial is associated to each sub-interval. To decrease the number of polynomial coefficients to store in memory, a non-uniform segmentation can be used. Smaller intervals are used for the irregular parts of the function. Significantly fewer methods are available for multivariate functions. Existing techniques propose linear approximation of bivariate functions. In this work, we propose a polynomial approximation for software implementation of bivariate functions. This approach is based on the mean-square minimization method. A smart non-uniform segmentation is proposed to better fit irregularities of the approximated function. Furthermore, to improve the performances, the degree of the bivariate approximating polynomial is adapted for each subset which avoid data and evaluation time waste. The proposed approach is composed of two elements. The first element is the technique proposed to determine the polynomials used to approximate the desired function f and to decompose the initial set into subsets in order to satisfy the maximal approximation error criterion. The second element is an optimized C source code which implements this approximation technique targeting real-time embedded systems. Now, we will present our approach. First, we define how the coefficients of the polynomial are determined. Our approach is based on the minimization of the mean square error. A rectangular set of the input space is uniformly sampled with endpoints pi having xi and yi as coordinate. We define f the vector containing the values of the function f for each point pi. We define the bivariate polynomial p to approximate the function f. This polynomial is a weighted sum of the bivariate monomials mj. The term cj is the weight of the sum corresponding to the coefficient of the polynomial p. The term c is the vector containing the different coefficients cj for the polynomial p. The goal is to find the optimized vector c tilde which minimizes the approximation error EMSE between the function f and the polynomial p. The minimum mean square error method is used to minimize the approximation error. The minimal mean square error of the approximation of the function f by the polynomial p is obtained for the vector c tilde with the following expression. The goal is to minimize the approximation error. So this error is compared to the maximal error epsilon that can be tolerated. If this error is higher than the maximal error epsilon, two strategies can be considered. The first one is to increase the polynomial degree d. This will increase the number of operations to execute and the number of coefficients to store in memory. The second approach is to segment the set E to reduce its size. The set E is split in several subsets and a dedicated polynomial is associated to each subset. For this, the MMSE method is applied on each subset to solve the minimization problem. For the proposed technique, the segmentation is implemented as a 4 regular quadrant splitting for performances and implementation ease. The segmentation can be applied recursively on one or several subsets. The segmentation scheme becomes then a non-uniform segmentation which is described with a quadtree, like illustrated in the proposed example. A polynomial pk described through a coefficients vector is associated to each leaf k of the tree. The degree of each polynomial pk can be different, so the length of the coefficient vector is dynamic according to the considered subset. Now, we will present the algorithm to implement this segmentation method. A recursive algorithm is developed to segment the set E into subsets. The inputs of this algorithm are the function f to approximate, the set E corresponding to the domain on which f is evaluated, a maximal approximation error criterion epsilon, and the maximal degree d max of the polynomial p. As described in line 4 to 6, the polynomial having the minimal degree and satisfying the maximal error criterion epsilon is determined. This polynomial is saved in the tree as depicted in line height. If the maximal degree d max is reached and the maximal error criterion is not satisfied, the set is segmented in 4 subsets E sub. The same procedure is applied for each of the 4 subset E sub as described in line 10 and 11. The recursive algorithm stops when the maximal error criterion is satisfied. Now we will present the global system to evaluate a bivariate function. The processing can be distinguished in 2 categories of tasks: the tasks done at design time and those achieved at execution time. For the tasks done at design time, the goal is to generate, only once, all the information required to evaluate the polynomial at execution time. Firstly, the recursive algorithm proposed in the previous slide is used to provide the quad tree describing the segmentation of the space E, to approximate the function f, with an approximation error lower than epsilon, and for the maximum polynomial degree d max. Secondly, the design space is explored by testing different maximum polynomial degrees d max. The solution leading to the best trade-off for the designer is retained, and thirdly, the tables containing the different polynomial coefficients are generated. These steps are done only once for a given function and parameters e and epsilon. Now at execution time, the approximation of the function f is done with 2 steps. The first step aims at finding the subset containing the tested values x and y. Currently, this step is achieved with successive conditional tests. But to be more efficient, this step can be achieved by analyzing the most significant bits of x and y. We will do it in future works. This step allows defining the index in the table where the polynomial coefficients, associated to the considered subset, are stored. The second step corresponds to the evaluation of the polynomial from the values of x, y, and the coefficients. Now, we will present some results of experiments. To illustrate our approach, the bivariate-functions function is considered. This function is plotted for values of x and y in the range of -3 to 3. This function is hard to evaluate with classical mathematical libraries as libm due to the presence of exponential and square functions. To illustrate the segmentation, a maximal error criterion epsilon is set to 5, 10 to the -3. On the left, the results of segmentation are provided for a maximal polynomial degree of 2 and on the right for a maximal polynomial degree of 3. These results show that for a given polynomial degree, the subsets are smaller in the region with higher irregularities. When smaller degrees are considered, like in the figure on the left, smaller subset are required to satisfy the criterion epsilon. Different tests have been performed on an ARM Cortex-A53 processor. The figure depicts the memory footprint and the polynomial evaluation time obtained for different values of the maximum polynomial degree Dmax. When Dmax is small, the segmentation is very fine in order to satisfy the error criterion. This fine segmentation needs a lot of memory to be represented. The evaluation time is on the contrary small because there are few coefficients. When Dmax increases, the memory footprint decreases but at the expense of a higher polynomial evaluation time. Once Dmax is greater or equal to 5, the model does not change because the minimum of memory footprint is reached. By modifying the maximum polynomial degree Dmax, the designer can explore the trade-off between the memory footprint and the polynomial evaluation time. In this presentation, we have described an adaptive technique for efficient polynomial approximation of bivariate functions. A non-uniform segmentation strategy and a dynamic degree solution are used to limit the implementation cost. The software implementation shows the efficiency of the proposed technique. This implementation uses floating point arithmetic for both segmentation tree traversal and coefficient encoding. In future works, the approach can be improved by considering fixed point arithmetic. Thank you for your attention.